Welcome, everyone. Okay, let's jump right in. Today, we're going to unpack the fascinating, totally invisible architecture that organizes, well, pretty much everything in our digital world. We're talking about the tree data structure. Honestly, if you've ever felt completely overwhelmed by the sheer amount of data out there, you're going to love how elegantly this structure handles the whole shebang. We've got a great roadmap for this explainer today. We'll be hitting trees in the real world, the anatomy of a binary tree, depth-first search, breadth-first search, and finally, wrapping up with time and space complexity. Let's get to it. All right, starting off with section 1, trees in the real world. So think about your laptop or your phone for a second. Have you ever wondered how your operating system doesn't just completely freeze up when you search for one specific document hidden deep, deep down inside folders within folders? I mean, with literally millions of files on a modern hard drive, a simple flat list just wouldn't cut it. No way. Well, the secret sauce here is that your computer uses a hierarchical tree structure. Pretty much every file system is organized exactly like this. The root directory, like your C drive, is the absolute starting point. And from there, folders and files act as child nodes branching outward. This specific structure is what makes incredibly fast organization and retrieval possible. You're essentially navigating a massive, invisible tree every single time you open a folder. Kind of mind-blowing, right? Okay, moving on to section 2, anatomy of a binary tree. Now take a look at this. It brilliantly illustrates the foundational building block of our entire system, the tree node. A tree is just a collection of these individual nodes. Each node holds on to its data, that's its value, and then it has references to its child nodes. Since we're specifically looking at a binary tree here, each node connects to a maximum of 2 children, a left child and a right child. It's wonderfully simple on its own, but man, when you string them together, they create some incredible complexity. As you connect these nodes via directed edges, those are the lines you see pointing downwards, you start forming subtrees. Suddenly you've got this full, rich structure with really distinct parts. You'll spot intermediate nodes in there, which are the ones that have both a parent sitting above them and children hanging below them. So we really got to get the lingo down for this. Keep these terms in your back pocket, okay? The root is the absolute topmost node, literally the only guy without a parent. The leaves are the bottom nodes with 0 children. They're the end of the line. Edges are just the connections pointing from a parent to a child. And this is absolutely crucial for the search algorithms we're about to look at. Depth is the number of edges from the root down to a specific node, while height measures the longest possible path from the root all the way down to a leaf. Which brings us right to section 3, going deep with depth-first search. Notice the path of the orange arrows here. Depth-first search, or DFS, is an aggressive explorer. It starts at the root and just charges as far down a single branch as humanly possible. It dives all the way down that left side, hits a leaf, and only then does it backtrack up slightly to check out the next available branch. It's all about going deep before it even thinks about going wide. And what's really wild is how that aggressive deep diving strategy translates beautifully into literally just 5 lines of recursive Python code. Look at this. We pass in a node. If it's empty, we return. Otherwise, we process the node, and then the function calls itself again on the left child, and then again on the right child. Actually, it's this recursion that inherently relies on your computer's call stack to handle all that backtracking behavior automatically. It's super elegant. Now, depending on exactly when you choose to process the node within that recursive code, you end up with 3 distinct traversal orders. Preorder is the one you'll see most often. You process the current node immediately, then dive left, then right. Inorder processes the left side first, then the node itself, then the right, which effectively reads a binary search tree from left to right. And postorder is a bit rarer. It saves the root processing for the very end, only after both subtrees are totally explored. All right, let's flip the script. Section 4, going wide with breadth-first search. So if DFS was our aggressive deep sea diver, breadth-first search, or BFS, is more like a methodical scanner. Check out the horizontal scan happening here. Instead of plunging down a single path, BFS traverses the nodes level by level. It looks at the root, then it scans perfectly across the entire next row of children from left to right, and it doesn't drop down to the next depth until that entire level is completely finished. It goes wide for sure. To pull off this level-by-level sweep, BFS actually completely abandons that recursion we just talked about. Instead, it uses an iterative queue system. Think of it kind of like waiting in line at a coffee shop. We use a double-ended queue. First, we put the root in the line. Then, as long as there are nodes in the queue, we pop the first one out of the front, process it, and push its left and right children to the back of the line. First in, first out. That simple rule guarantees we finish a whole level before we even touch the children on the next level.
Let's wrap this all up with Section 5, time and space complexity. So putting these two heavyweight algorithms head-to-head, the first thing you'll probably notice is that time complexity is a dead tie. Both DFS and BFS visit every single node exactly once, which gives us an O of n time complexity, where n is just the total number of nodes. But here is the real game changer. The space complexity is where they wildly differ. See, DFS uses the recursive call stack, so its space is limited by h, the max height of the tree. If your tree is relatively balanced, that is incredibly efficient. BFS, on the other hand, has a queue that might need to store an entire bottom level of the tree all at once. In the worst-case scenario, the bottom level holds roughly half of all the nodes in the entire tree, blowing its space complexity up to O of n. So, next time you're furiously clicking through folders, desperately trying to find that one specific file, just take a second to appreciate the magnificent, completely invisible tree structure that's organizing all that chaos. It's actively processing your request using these beautiful traversal algorithms in mere fractions of a second. Which kind of leaves us with one final thought to chew on. Beyond just your computer's file system, how many other massive, invisible tree structures do you think are quietly organizing the apps and websites you navigate every single day, without you even noticing? Thanks so much for joining me for this explainer, and keep exploring.